Okay, but don't forget what we said about the symbols, because we need to be using the symbols. These are the symbols. You need to use them. When it is fixed, a fixed resistor, it has one particular value of resistance. If it's a variable resistor, it can have several values of resistance. You can set them to different values of resistance. And a voltmeter that is used to measure voltage across. An ammeter used to measure current. The current is measured in amps. The voltage is measured in volts. I should have told you that. And of course, a cell has just one short stroke and a longer stroke. The short stroke is the negative side. The long stroke is the positive side. Do you know? Okay. The short stroke is negative side. The long stroke is the positive side. So that's a cell. But if you have two or more cells, you call it a battery. This is the battery of two cells. This one is a battery of many cells, because there could be many cells in between here. And I told you what a resistance is. Don't forget. Resistance is the obstruction or opposition to the flow of current. If you have a high resistance, it means lower current will flow. So that's why you answered all this. The current is small because it is harder to travel through both bulbs. So we said there's a high resistance. And the current does not get used up. As it travels around the circuit, the ammeter gives the same reading everywhere in the circuit. So in a series circuit, current is the same everywhere. Everywhere in series has the same current. The reason is it is the same current that flows through all the components in series. After all, the current doesn't enter to another route, does it? It can only flow through one route. Scroll up a bit to reveal the diagram properly. The current can only flow through one route. So its current is the same everywhere in series. What did I say?
Current is the same everywhere in series.
I think I have to look for a small place to write it down. Let me zoom in and write it. Current is the same everywhere in series. Can it fit in here? Okay. Everywhere in series. In series, because the same kind of current that flows. Read what I wrote. Read it out.
Current is the same everywhere in series.
So long as it is the same route, it didn't branch off, it's the same amount of current that flows through. What's the current flowing through here? As you can see in this diagram. Are you seeing what I'm circling? 3 amps. So if you place an ammeter anywhere in series, like you place an ammeter here, it will also measure 3 amps. The ammeter here will also be 3 amps. If you place an ammeter here, it will also measure 3 amps. Because it's the same current that is flowing. It didn't branch to another place. Okay? So current is the same everywhere in series. It's the same current that flows through. That's what you answered here. It says the ammeter gives the same reading everywhere in the circuit because it's in series. But it is not always like that in another kind of circuit connection we call parallel. Because in parallel, the current gets into a junction and then splits. Some will flow through this path, another will flow through this path. They don't even have to be the same. I will deliberately make this one, give it a different value of current, so it doesn't look like it must be the same. So I will call it 2 amps.
Wait, why?
I just decided to call that. It could be the same current, but it doesn't have to be. Because when current flows into this junction, let's call this junction P. I'm going to call it junction P. It splits at this junction P. Some will flow through here. What value of current is flowing through here? 3 amps. The rest will flow through here. What value of current is flowing through this other one?
2 amps.
They will meet up again at another junction Q where they will combine. And when they combine, they continue their journey.
That makes 5 amps, and up here is
Okay,
6 amps.
so let's change it. I want to change it. I like that you've observed that this should be 5 amps. So let's change it for the purpose of our illustration. So this will make here 5 amps. And make here 5 amps. So we can start to change the diagram slightly. It's our own diagram. It's also 5 amps. That already tells you that the current, total current that flows into a junction must be equal to total current that flows out of the junction, is it not? Did you hear me? What's the amount of current flowing into this junction?
3.
No, flowing into the junction, as you can see.
5.
So when you add up all the current flowing out of the junction, what will it give you?
Wait.
I mean,
including the 2.
I mean, this one 3 amps, this one 2 amps, these two of them will give you how many amps?
5.
So total current flowing into a junction is equal to the total current flowing out of the junction, isn't it? It's equal to. So can I write that down? Let me note it down here. In a series in a parallel circuit, what kind of color can I use? Please go to the right, top right. That's where I'm writing it. In a parallel circuit, the total current into a junction or entering a junction, let me use a simpler word. The total current entering into a junction is equal to the total current flowing out of the junction. Read out what I wrote in blue.
In a parallel circuit, the total current entering into a junction is equal to the current flowing out of the junction.
So the total current entering into a junction is equal to total current flowing out of the junction. Take note of this. When they meet at the next junction, they combine again and flow out. Can you see why here is 5 amps? Scroll down to see what I'm showing. Here is 5 amps because they combined. This one 3 came to Q, 2 came to Q. They combined and became 5 amps. It's the same 5 amps that flows all through. If I had an ammeter here, what would be the reading of this ammeter here? Yes, what would be the reading of that ammeter there?
the whole thing.
This place, what would be the reading of the ammeter here?
Wait, so what would have happened is would it have done this? So it would have skipped this one here.
Yes, remember it can flow through the inner loop.
So it will
Or
you
if
just
you
add
flow.
up this one.
No, what I'm saying, what is the current in this new ammeter I've introduced here? Do you know it's the same current that entered at the 2 amps that is also flowing through the new ammeter?
Is it 7?
No, I'm asking for the current only in the ammeter. The same current that is entering the 2 amps is the same current that is flowing through the ammeter. It didn't branch to anywhere. Did you hear me? This same current flowing through the 2 amps is the same current that's entering the. So it's 2 amps because they are both those two positions are in series. So it's also 2 amps. 2 amps. If I added an ammeter here, let me make it smaller. What will be the value of this current here? Okay, go ahead and answer. What will be the value of the current here? 3 amps, because it's the same 3 amps that flowed into here that will get to here. So this will be 3 amps too. So 3 amps into this root, 2 amps into this root, they meet up again and became 5 amps, continue their journey, or 5 amps until they meet the junction again. Don't forget that in a parallel circuit, the total current that enters a junction is equal to the total current that's flowing out of the junction. Is that understood? Okay. All right.
So,
I'm listening.
So would it be this to this to this? So would it be this one here plus this one here and plus this one here?
No, not really. Everything on this path is treated as the same thing. 3 is the same current. Also, everything on this path is treated as the same current. 2. So 3,
So this one here.
2, all add up to give 5.
So you do add this one. I thought you added this one the whole time.
No, this one hasn't splitted. It's still flowing in. It's when it splits that you now begin to separate. 5 enters, 3 enters. 5 is entering in. 3 came out of it, went through here. The remaining 2 came out of it, went through here. They meet up again and became 5, and the journey continues. Does it make sense? Okay. That's about that. Now, there's something you need to know about parallel circuits. Voltage is the same everywhere in parallel. What did I say?
Voltage is the same everywhere.
There's something that is the same everywhere in series. What is that?
The current.
Current is the same everywhere that is in series. We have the same amount of current. But when you come to parallel, there's something else that will be the same. That's voltage. I will have to note it down somewhere. Voltage is the same everywhere in parallel. Let me note it down in a yellow pen. Voltage is the same everywhere in parallel. So you will now understand what instrument do we use for measuring current again?
An ammeter.
What is the same everywhere in series?
Current.
Now, because current is the same everywhere in series, and we use an ammeter to measure current, it means we need to connect the ammeter in series. Ammeters are connected in series. Read what I wrote.
Ammeters are connected in series.
The reason is because they are measuring current, and current is the same everywhere in series. If you want to connect ammeter, it should be in series like this. It should just be in the same end to end. But if you want to connect a voltmeter, you have to connect it in parallel. I will explain that later, maybe in the next block. Read what I wrote in yellow. Scroll down to the right hand side.
Pardon?
Read what I wrote in yellow. It's on the right hand side.
Voltage is the same everywhere in parallel.
So what instrument do we use for measuring voltage?
The voltmeter.
Therefore, a voltmeter, because it measures voltage that is the same everywhere in parallel, a voltmeter is connected in parallel. How is a voltmeter connected?
Voltmeter is connected in parallel.
Why?
Because the voltage is the same everywhere.
Because the voltage is the same everywhere in parallel. How is an ammeter connected?
The ammeter is connected in series because the current is the same everywhere in series.
An ammeter is connected in series because the current is the same everywhere in series.
Mr. Joe,
Yes.
can I quickly go to the toilet?
All right, please. I need you to come back as quickly as possible.
Okay.
Okay. So it says both bulbs are connected directly across the two batteries. Therefore, they are giving the full okay. A voltmeter, both bulbs are connected directly across the two batteries. Therefore, they are giving the full what? What is the same everywhere in parallel? Because these bulbs are in parallel. So they are giving this full voltage. The current is larger because it is easier for it to flow around the circuit. If another bulb was connected in parallel, they would still be as bright. That's correct. Because the same Okay.